in? Okay. Well, if you look at your photos, you'll see that we're in that upstream area where the stream was quite unstable from a sediment perspective. It had erosion, it had active erosion, and the banks were slumping and falling in, and the channel was really trying to work out a wider floodplain on its own. And really that's what streams do, they're in size. So I'll try to talk as loud as I can, bear with me. Jason Zink is the PE who designed this. He works with us at Cooperative Extension in North Carolina, and we're going to talk about this structure in just a minute. But what we're really looking at is energy management, managing the high flow coming through here. So this stream is a multi-stage channel, and today you're looking at base flow. You're looking at the low flow condition when there hasn't been any rain. Well, a little bit of rain yesterday, but not enough to generate a flood. It maybe came up that much. And base flow, it's always easy to come out and look at the stream and say, well, the stream is carrying that flow. I don't see erosion. I don't see any problems. I don't see deposition. But when we come out in the middle of a big flood and that water is blasting out of that culvert, is really what we need to design for. That is the high flow condition, the flood condition, when all the work is being done, all the erosive energy is in the stream. So, Jason, I'll turn it over to you to talk about this cross vane, and we'll talk about the dimensions, the size of it, and we'll also talk about the habitat values of the cross veins.
So this is a boulder cross vane we're standing at, and it's placed here for 3 reasons. First is to provide grade control in the stream, as we've already talked about, so that the stream bed doesn't cut down. You can imagine we have all this flow coming through the culvert. If we didn't have a fixed point here in the bed, that erosive force could easily erode this bed out, and you end up with a waterfall coming out of the culvert. So it's fairly typical in a case like this to install a grade control structure just downstream of a culvert. So that was done for grade control, is the first reason. The second reason is to protect the stream banks around here. Imagine what happens when you have a flood flow coming through the culvert. It's going to encounter this vane. Water is going to run up this arm. This arm is sloped up at about 5%. That water is going to slow down and turn back in toward the channel. That's going to happen on both sides. So flood flow is going to converge toward the middle of the channel and keep stress off of this bank and especially that bank. And that's very important in this case because back in June, when we took the equipment out of here, the day after we finished construction, there was no grass growing on these banks. We had them graded, matted, seeded, but they're very susceptible to high flows until we get some deep-rooted vegetation established. So we have grade control, we have bank protection, and the third reason why we put this here is to provide some habitat value through having a scour pool in here. That convergence of flow keeps this pool scoured out, and in fact, 6 months after construction, it's still fairly deep in here. We've got...
Yeah, here we go. It's about 2 feet deep.
You have a big 2-foot deep pool that's providing some bed diversity throughout this system. So those are the 3 reasons we put this structure in here. And I'll tell you now a little bit about how we did it. I told you that we tried to slope these arms up at about 5%. 5% from this point to the end of that boulder. And when we get further down away from the road noise, we'll actually measure an arm on a different structure, and I'll show you how we measure that 5%. We also have these arms at an angle out from the bank of about 20 to 30 degrees. If this arm protruded too much in, say greater than 30 degrees, you'd be setting yourself up for some possible bank erosion here. But we found that this arm angle is optimal for converging the water and getting the flow downstream. There's more than just this one layer of boulders here. There's a second layer of boulders under the water surface. So when we built this, the crew excavated a big hole here and put down first this footer layer of boulders in the shape of the cross vane. Why did we do that? Well, this stream is not going to transport these boulders downstream. It just can't, it doesn't have the power to do that. But what it can do is erode that sand and clay material out from under the boulders, and your boulders fall into the stream. That's how a structure like this can fail. So by putting this footer boulder in here all the way around, you're protecting yourself against these boulders being undermined and falling in. So we have these two layers of boulders. You can see a little bit of fabric right here. This is a non-woven geotextile that we put behind each of the arms to keep water from piping through the arms and undermining these structures. So this piece of fabric goes down a couple feet and comes back toward where you're standing, and it's backfilled with gravel and small cobble material. Let's talk about the tow-wood.
All right, good. So Jason described the boulder vane, the cross vane, and boulder vanes have been used for at least 20 years. Back in the early 90s, you saw some experts in stream rehabilitation start to use this form of weir. It's really a weir. It's a grade control structure. It's providing a flow path, and they started using those primarily in the western U.S. And then in the mid to late 90s, we saw more of these coming into Georgia and other states in the southeast. And I think we learned a whole lot about how to orient these, like Jason described, how to build them, how to keep them such that they don't move. And that's something that's important. What he described, the construction process, it's important that everything be built so that they don't ever move. Because if we lose one of these boulders, if it slides or shifts or moves, we could have a head cut move around it, through it, and then we'd lose the purpose of the structure. So this is a very well built structure. We could say now that we like it after it's been through a few floods. Another part of this, you know how quiet it was when you were talking, and now they're back. But Jason mentioned the pool, and we always like to see large pools in a stream like this because we get a lot of energy dissipation. The water comes rushing through, it gets in here, and it starts to spin around. We get those eddies, and then it drops out some of the materials with it, and then it continues on down through a riffle. So we have step, pool, riffle, and then step, pool, riffle, and that carries all the way down through the valley. In the pool, you see the leaf material. Can anybody see that? Yeah. Veronica can see it. So who likes leaves in a creek? Who's a big fan of leaf material in a creek? Okay, well, good. Because when you get down there to hear about the bugs, wherever Duncan is and Eve, maybe they'll be talking about the value of leaf material, and if they forget, say, what about all these leaves in here? Is that a good thing? Is it good to retain leaf material in the creek? Yes. The more vegetation, the better. Well, behind me is what we call tow wood. By the way, if anybody wants to get in here, this is fun. It's like when you're a kid, you got this, it's all mucky and oozy, and take your shoes off. It'd be a good day for that, but I'm not seeing it. You could earn bonus points. Well, behind me is an element, a bank revetment that we call tow wood. Now, in the past, we might have used a lot of root wads. Anybody here ever designed or constructed a root wad? Right. This project has 0 root wads. Are you surprised, Diana? A little bit? Yeah, we could have lined this bank with root wads. We basically take the tree root and anchor it into the bank, and then we have this big root mass sticking out. And those things can be pretty effective as a revetment. They could even catch some of the leaf material, and they provide a place where the energy is dissipated and it moves on down valley. And we could have done that, but we wanted to try this new idea that's been around now for about 2 years called tow wood, and it's really nothing special. It's just we take a bunch of tree branches and large chunks of wood, and we bury them as deep as possible. So they go down to about 3 feet below water, and then we put soil on top and we plant live living trees on top. And then what sticks out are all of these branches and they're dead. By the way, tow wood is dead wood. So we have these pieces of tree sticking out, and you see already they're catching some leaf packs, and there's some habitat value there, and it's what you would see in a natural stream where you do have trees falling in, branches falling in, and it adds wood to the system. It provides diversity and habitat, and it's one of those ecological values that it's hard for engineers to get through because this is kind of fuzzy, right? And you know, the Army Corps and other agencies have been spending money for years to snag wood out of the creeks, and here we are sticking it back in. So we have to be a little careful how we do that. We don't want to create an obstruction at this point because we do want the flow to continue on down through here. We don't want a major obstruction that'll lead to big bank erosion, but we do want to add more wood and more leaf material and more habitat to the stream.
So how far is your tow wood?
The tow wood extends from the boulder all the way down to there. And it's where the stream narrows back up into the riffle. So we have pool and then a glide out of the pool and then into the riffle, and we work on down valley. So it's a nice transition. We have multiple bed forms in this little system here. Instead of one long run of consistent bed form, we have a lot of diversity.
How far back is it tucked in your fill material?
It's about 5 or 6 feet.
Okay.
Yeah, the pool itself, we dig out about 3 feet deep. And then along the bank here, we're down at that depth and we start building layers of that wood. And we have large chunks of that wood and soil, and we compact all that, and it's back into the bank about 6 to 8 feet. And then we put the soil on top of that. You see the glide stakes and the trees planted here. We always want to plant trees. We want those living roots to come out here, and as that wood, some of that wood up high is going to decay pretty quickly. We want the living roots to come out and replace the dead wood. Now the wood that's underwater all year long, that'll stay there a very long time. Quite good? Let's walk on down to the next big structure. This is fun, isn't it?